So, continuing to talk about approximating solutions to differential equations, we can start to consider another thing called a slope field. So, to begin to think about this, we want to first consider what does dy dt tell you about the solution y of t? And to think about that is we know that that's the slope of the tangent line. So, with just the information about the differential equation, even if I can't look at it and solve for y of t exactly, I have complete information about the slope of the line tangent to y of t at my different points. So the idea of a slope field here is that we can get an idea of the general behavior of a solution y of t to the differential equation dy dt equals g of t comma y by looking at a plot of the slopes given by my differential equation dy dt equals g of t comma y at each point. And importantly, when we talk about such a plot, these plots are called slope fields. So one thing about slope fields that will be evident from me trying to do this next example is they're very difficult, very tedious to draw out by hand. Luckily, computers can generate very nice slope fields, and so some of the examples we look at will take advantage of that. But I do want to go through the process of drawing a very simple sketch so that it's clear exactly what the connection is here. So suppose I'm asked to sketch the slope field of the differential equation dy dt equals 1/4 y. Again, this is one that we could solve exactly, but let's disregard that entirely and just think about the notion of the slope field. So it, of course, is a little bit vague that we weren't told exactly which coordinate paired points to consider in plotting this. So I'm going to just assume we look at the first quadrant. And here we have my t and y axes, but what we plot here is going to be different from what we normally think about. Instead, at each point, I'll come back up to the picture here, but I'm going to sketch a dash, and each dash at the point ty represents the slope at the point ty. And again, by slope, I mean the slope of the tangent line. So to think about that here, let's consider some different possibilities. So first of all, if we focus on the horizontal axis, that's when y is equal to 0. So if I come back to my equation here, when y is 0, then dy dt is 0. So my slope is 0. So what we want to think about is, how would I sketch a line segment that had slope 0? Well, I would draw it perfectly horizontal. So to represent the slope at each of these values, I'm going to draw a horizontal line. One thing we can think about here is that what if we then move up to y equals 1? In that instance, the slope dy dt should be 1/4 times 1. And so I would expect a small positive slope. So what I should sketch here is some line segment that has a positive slope. And I should draw the same line segment everywhere where y is 1 because they all have exactly the same slope. When I get to y equals 2, now my slope is 1/2. So that should be slightly more positive, and again, identical as I move along here. If I get to y equals 3, then I have slope 3/4. And so what you can see here is these are all relative. So if I go up to 4, even more steep. And of course, the thing that gets difficult is the way that I represent a slope of 1 versus somebody else can be difficult to kind of sync, but it's all relative to how I'm sketching the other ones. So one kind of connection we see here is that positive slopes, we should expect to see something that moves upward from left to right. If we're in a place where we have negative slopes, then we should expect to see dashes that move downward from left to right. Whenever the derivative is equal to 0, then we expect to see completely horizontal dashes. And we didn't really look at this here, but there could be instances where the denominator is 0, and we think about like an infinite slope. So then you would have completely vertical dashes. And then finally, like I said, comparatively steeper slopes are either more negative or more positive than comparatively flatter slopes. So what we can get out of this here is, like I said, even though we can solve this solution for a solution, from what we've seen before, we know that the general solution of dy dt equals 1/4 y should be some constant multiple of e to the t over 4. But even if I didn't notice that, look at how I can get some kind of notion of a solution function that kind of matches that pattern. So in particular, if I were to give an extra piece of information that this function, solution function, passes through the point 0, 1. Well, in order to think about the solution, I can kind of follow these dashes in order to sketch out a solution. And what we can get from that is, even though I don't have a specific function, one thing I could see here is that that function would always be increasing. I could see that as I send t to infinity, I would expect that function to approach infinity. So we get some kind of qualitative aspects from that. And that's the nice thing about slope fields in general.